Today I wanted to talk about a multi-stage problem. And the reason I want to talk about this is we did graphing for a couple of days. Now I want to go back and kind of hit some of those word problems, see what you've forgotten. And after we do a couple of these two-stage problems, then we'll come back. And if you have any questions about graphing, we could revisit that one more time. And don't forget, you have a quiz coming Wednesday on this stuff, the one-dimensional motion, which is chapter 3 in OpenStax, but chapter 2 in our workbook. So quiz on Wednesday at the start of class. All right, so that said, I'm gonna look, I'll start with a quick screen share. Maybe, there we go. It's taking its time here. Okay, there we go. Let me make sure this is plugged in. Yeah, it is. All right. So I'm going to look at 2.6. Okay, so 2.6 is what we're going to look at. This one. I'll give you a second to look at it while I get the board and stuff ready. And you can imagine, try and remember your strategy, your problem-solving strategy. What are the steps that you do? Hopefully the first thing you think is try to draw it. Oh, read. That helps too. Read, draw, label, list, equations and unknowns and stuff. Okay. So we have a driver. It's going with some constant speed. Uh-oh, my marker's dead. That's no good. The driver sees a deer some distance away. Okay, so that distance is D. The driver is going at some speed V. After taking time TR to react, he applies the brakes and slows. And then what minimum rate of slowing will cause the car to stop before hitting the deer? All right, so let's get this up. Okay, so you've got this deer. So this is what I started with, and then I'm like, wait a minute. At some point, this driver applies the brakes. So at some point, we need another special spot in here. And at this instant, the person starts applying the brakes, and eventually they stop just before hitting the deer. Okay. So these are all the pieces of information that we're told. And so I guess something I might ask you is, what is the speed at the start of this stage right here? He's reacting, or she is reacting, hits the brakes right here, or starts to hit the brakes. What is the speed at this instant when just as they start to hit the brakes? In terms of the letter V, is it bigger than V, less than V, or equal to V?
V.
V, exactly. So they haven't had much time to brake yet. So the second they first touch the pedal, shouldn't they still be going exactly the same rate? And then what's the velocity over here at the end?
Zero.
Zero, because you're stopped. All right. And so what we want to do is we want to find a way to keep track of these stages. All right. And so in this case, I might call this, all of this up to right here, stage 1. And all of this crap over here, stage 2. And what we see is the final velocity at the end of stage 1 is the initial velocity for stage 2. That's going to show up in our list of stuff. And so I'm going to write down a list of knowns and unknowns. So let's say we have delta x for stage 1. I'm going to put a subscript 1 on everything now. I've got v1 initial in the x, v1 final in the x, a1 in the x, and time 1. These do not necessarily have the same amount of time. So right now I have I have a list of knowns for this thing, and I'll do the same over here. Do you have to do it this way? No. But does it help most students get the answers more often? I think so. And not everybody thinks the same way, so don't assume this has to work for you. But one of the things I find is as the problems get harder and harder, the more important subscripts are. Basically, you need a way to stay organized. So notice I'm color coding, I'm splitting them up on the page. I'm trying to be very clear about stuff that belongs in stage 1 and stage 2. Find your own way of doing that. Here's a couple of suggestions. My main one is subscripts, because then you can just do it all in pencil. The second would be to add color if you want. If you're working on OneNote or something, or if you have one of those pens with 4 colors, you could do that. Or even have pencil and pen, right? Anything to keep the 2 stages unique. So in this case, do I know x1? Is it a known or is it not known? What do you think? Go ahead. Let me ask you this. Is x1 the distance traveled in stage 1, or the displacement in stage 1? I should be careful. I said distance and displacement. They can be used interchangeably for this problem because everything's going to the right and it never reverses direction. But strictly speaking, this is displacement, not distance. Is this distance d or is it not d? Again, in stage 1, oh, go ahead.
Jumps is not D.
Not D. We don't know what it is. It should be less than D, right? Because it's not the whole thing. Huh, that stinks. Well, what about x2? Is that equal to D? It's also unknown. All right, so that doesn't help too much. Let's go down here. How about V initial x in stage 1? That one was given to us as V. Remember, because V was given in the problem, this is a known. So you have to assume that you know that. V1 final is equal to, well, let's skip down here to A. What's the acceleration assumed for stage 1 and why? What do you think? What's the acceleration there? Oh, sorry, it kind of computered out there. What was that?
Oh, it's a 0.
Yeah, it's 0. What's the words in the problem that help you see that?
Constant.
Yep, constant speed.
Constant speed.
Nice job, nice. And so doesn't that also mean this is V? Now, wait a minute. What's the time for stage 1? Do we know that, or is that not known? What do you think?
Would it be TR?
It is TR. And so that is something that we supposedly know. All right. And so out of all this, I think we could probably use these pieces of information down here to figure out that thing. Agreed? There's probably some equation. It's probably this one. if I have this equation, this goes to 0. I know this is V, this is TR. Aha, I just figured this out. I'm going to make these blue just so they stand out. So that helps me figure out, aha, this unknown up there. All right, let's go over here into this stage now and go through here. Well, V2 initial is somebody else. What do you think? What's V2 initial in this case? I want V2 initial in the X. That's the start of stage 2. We'll get a V there.
B.
Oh, sorry, my bad. Zoom is such a terrible medium for this interaction. My bad. Oh, and there's a bunch in the chat too. Maybe I've been missing that. Oh, yes. Oh, thanks. Thanks, Jay. You're saving me there. I forgot. I'm a little spaced out. It is a Monday, right? Oh, you guys are doing a great job putting it in the chat. So that's cool. Thank you. Sorry, I just screwed up. I forgot I was on Zoom for a minute. All right. So V2 final. What do you think that's going to be? I got the chat up if you want to dump it in the chat too.
0.
0. Thanks. A2X. Is that going to be 0 or something else?
It's going to be something negative, right?
We expect it to be negative because you're going from a positive velocity to 0. So it's an unknown. We expect a negative number. And I believe, is that what we're supposed to be finding? It says rate of slowing. This is WTF, what to find. Okay, so that's what we're looking for. Nice job, everybody. T2, do I have that or not? I didn't see anything in there. I'm going to say unknown. So take a look at this trick. It's not that much different than the usual problems we had. Remember, we had a problem before where you'd have a list of things and then there'd be 2 question marks. So now what do we have? We have 2 problems. This one only had 1 question mark and this one has 3, but on average, aren't there 2 question marks per list? So it's the same kind of problem, but they just mix up what you know and don't know here. So in this case, this problem is going to be impossible to solve because we have 3 unknowns unless we can get one more piece of information. Which one of these question marks can we actually figure out using this information?
Delta X2?
Exactly. So what is the connection between delta X2 and this side over here? Can you say it in an equation form?
So since we know the total is D and we already know the value for delta X1, it'd be D minus VTR, correct?
Yeah. How about I think you said that correctly, but I'm going to say it this way up here at the top. I hope this is still in there. Let me get just a hair. I'm going to say we know that this is D, right? Isn't that equal to delta X1 plus delta X2? And so what he was doing is he did all the algebra in his head, which is great. And you could do that at this level if you want. However, I think it's better to first write equations. And this is, you could think of this as being our very first constraint equation. So constraint equations are very useful in engineering, where basically you say, all right, I don't care how this job gets done, but I do know that the total output needs to cover this distance. All right, so make sure that happens. That's a constraint on an engineering problem. You're saying, as long as you don't hit that deer, we're good. Now, there could be other constraints like having an acceleration that doesn't kill the driver. That would be a nice constraint as well. So there's, right, but yeah, you could have all these different constraint equations for an engineering problem, and then you find a solution that meets all of the different constraints. So that's how I'd kind of like to think about it. I don't know who chimed in, but that was a great job. So what he was saying is, wait a minute, isn't this just, let's see, x1 is VTR right here. So this thing right here is V times TR. And so what he was saying is, I believe this is D minus VTR. And is that what you said?
Yeah.
Nice job. Nice. I'm going to pause for a second to make sure everybody's cool with that, if there's any questions there. So again, this was just saying the two stages have to add up. Notice this was not given to you. You're expected to figure that out in a physics class. Okay. All right. So sometimes a physics problem will say the time for each stage, and then you have to know, oh, the total time is add them up. Sometimes it's the total distance is add up the distances, things like that. You're kind of expected to be able to do. All right. And so then at this point, I'm totally running out of room. So what I'm going to do is we've pretty much used everything from stage one now. I don't need it. Normally, I would not erase this and start working here. I would work down the page. So for you guys, maybe just keep working down on this side of the paper that you're working on. Whereas I'm going to have to go over here. And just for expediency, I'm not going to erase it and switch it over here. But I do know that. And let's see, what else do we know? And finally, so there's my equations. Apologies if they're a little small there. I'll scoot in a little bit. And so what's something we might do right away? There's lots of different things. So go ahead, say anything that you think of. What would you do next?
Input the zeros.
Yeah, I like putting in that 0 just because maybe it'll make things more obvious. So that's here and here. That's nice, getting rid of that. I think that's it. All right, so what might we do next before we plug in blindly?
Pick one and solve it algebraically.
Yeah, which one? I would first, okay, so that's a good thought, right? At this point, there's lots of ways to pursue, and basically you got to do algebra, right? I would stick in that extra step of which one might be the easiest algebra before I waste a lot of time. So you don't have to write them out to do this, but you could just look at the equation sheet and just kind of think through it. I'm guessing this one's the best, because don't we know this is known, right? And we know this, and this is what's to find. To me, that seems good, but let's check this one. I know this. Don't know, bad. I know this in theory, right? We know all of these. These are givens. I know this. I don't know that. Don't know that. This is the worst. So yeah, I would grab one and solve it. And this one, take a look. I could take this equation, solve it, and figure out A. And like we said, we're expecting a negative number. Well, when you stick this in, I think it's going to be a negative number. That's cool. Number two, I could then take that A and stick it in here and solve for T without too much trouble. Good. Finally, I could use this to check and make sure both answers match each other, and that's time permitting. So the more practice you do, the faster you get, the more ways you have to check your answer. But if you don't practice enough, there's no way you have time to check your answers. So, all right. Before we look at the solutions, I'm going to skip to the solutions now and just see, unless there's questions while this is still up. Let me do a quick check. What do you think? Is this making some sense at all, or yes, no, maybe? Something? Okay, cool. Let's take a look. And so this is kind of what we were looking at. And I think that's pretty much exactly the same as what we thought. And so let's see here. Oh, so I did this a little bit differently. So I put okay, so this is the same thing, but what I did is I made the minus sign explicit. So I said negative A, where A would be the magnitude, or you could get A and expect it to be a negative number, either way. But so notice, because I did this, right? That's the sentence. So notice I did do this slightly differently. Let's pause and make sure this makes sense. Does anybody have any questions about that? I thought that was, it's similar, but it is slightly different. This was the connection between the two parts, so that was really cool. And remember, only in this problem where everything's moving the same way can we use distance and displacement interchangeably. Normally, we should always be using displacements. Okay, so there's that. And again, the minus sign looks a little weird, but that's because this is a magnitude in my problem, in my solution here. Okay, whoops. And then, okay, so there you go, blah, 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 blah. And so this gives you some reality checks and some problems. So there's the solution to plug it in. Oh, yeah. So it looks, this is crazy. Look at this. Performance vehicles can brake the same rate as free fall. Isn't that crazy? That's pretty wild. And so I try to do some reality checks here. So this is a good summary of how you might do a reality check. And so that's kind of the fun part, right? If you do these problems all algebraically, that's what allows you to think about it in a physicsy way afterwards. So it's not rocket science, it's just algebra. But the fun part afterwards is physics. All right, I'll leave it at that. So you guys could check that out later. Any questions so far? Anything at all about this stuff? How's that code going, Jay? Close?
So I got the balls in motion.
Sweet. I'm gonna. Oh, go ahead.
I got the balls in motion. I'm just trying to clean up the axis because
Yeah.
I
Okay.
just have the one axis.
I got
But
you.
I got the balls in motion, but I had to be a little creative with it.
Sure, that's fine. That's fine. Well, we're gonna start working on that 2.36 now. So you still got another 15 minutes, 20 minutes.
Sounds
All
good.
right. So
I'm just gonna clean it up a bit.
Sounds good. I gave Jay the challenge. She's trying to simulate the next problem that we're doing. And I didn't tell her about it till the minute before class started. So we'll see how it turns out. So that's the challenge for Jay. And then at any time you could discuss with her. But so let's get to the next problem, right? The faster we get the next problem, the more pressure we put on Jay, and that's more fun. So let's see what we can do here. So I want to try another one of these. This is a classic. These are called intercept problems. Page 41, problem number 2.36. I'll screen share. There we go. So we have a snail in a car driving here. He's going to pass a cop without noticing her. And then at the instant the speeder passes the cop accelerates from rest. For ease of communication, let's call the point where the cop and the speeder pass each other. That's the origin. All right, so this is called an intercept problem. It's very similar to what we just did. There's two things happening. It's a two-stage problem, right? You have a snail doing the snail thing, and then the cop doing the cop thing. And so I'm going to try and get a picture of this. Maybe you could see what you draw as a picture, maybe without looking at the solutions. Just try to draw a picture and see if your picture ends up looking like mine or not. Not that it has to. Okay. Going to go ahead and share the screen here. All right. And so here's the picture that I drew for part A of this question. It said, determine the maximum distance between these two. I think that's what it says in part A. What is the maximum distance between the cop and the speeder? So in my mind, this is what's going on. The speeder is S. Man, look at that S car go. One more blink should do it. There. Oh yeah. It doesn't work as well in Zoom. Usually you get the painful groans from students in class, but that's one of my favorite jokes. Look at that S car go. All right. Anyways, it's not going to get any funnier, so we might as well do the problem. All right. So I just chose to call the speeder or the snail number 1 and the cop number 2. And so in this case, the cop starts from rest, so V2 initial, and I dropped the X subscript since everything's moving in the X. Normally I would keep them on, but for this problem, I'm getting tired of putting X all the time. We'll need that more in the next chapter. So starting Wednesday, we'll do that again. The cop is accelerating, the speeder is not. And so in this case, we want to figure out this distance right here. That's what I'm looking for, the maximum distance between. So I guess I'm wondering 2 things from you guys. What is the speed of the speeder at the end or when they reach this maximum distance? What do you think? If the acceleration is 0, what is it going? Oh, and there's a chat there. Let me see. Oh, yeah. Oh, go ahead. Somebody unmute
Would it
there.
still be 30 since
now,
yeah,
careful.
miles per hour?
Is the snail going 30? Read the question carefully.
No.
They're driving at speed V in a 30 mile per hour zone. So we don't know that they're going 30. And in fact, we expect they should be going faster than 30. Otherwise, the cop's not going to go after them, is in theory how it should work. All right. So, yeah, let's say we got, so it's still V, but not necessarily 30. Does that make sense, Erica?
Yes.
Right on, right on. Okay, so now, since she chimed in, she doesn't have to do this one. Somebody else, what do you think the speed of the cop is? And this is kind of a weird physics fact that you might not know. Here's the issue. In this problem, we're told this is the maximum distance between them. You should be able, from that statement, because we're trying to figure out the maximum distance between them, that's supposed to tell you what this speed is. Take a guess. Is it going to be bigger than v, less than v, or equal to v?
Would it be equal to V?
Yes, and this is the tough part. So now you should be writing down something in your workbook or something that says anytime you get this max separation in an intercept problem, that's what tells you, hey, dude, the cop has gotten to the same speed as the speeder. Think about this. If the cop was going any slower, well, the distance between them would keep growing, right? If this one was going 20 miles an hour and this one's going 15, this one is still gaining ground at the rate of 5 miles per hour. Now, if this one was at 22 miles per hour and this one's at 20, this one is going to start gaining on that one and closing the gap. So at the exact moment when the cop's speed matches this speed, the distance between them isn't changing for a split second. That happens to be the maximum distance. The cop is no longer losing ground, and any later it's going to start gaining ground. Does that make sense? Why this has to be V? If you see the word something like what's the maximum distance between or maximum separation, that's the key words that makes you know this. Okay. And that's just, if you didn't know that, that's fine. I expect you to have that memorized for the rest of your life now. All right. So that's cool. All right. Just a weird new physics. I'm trying to give you all the words from the physics word problems that help you get that one last list, one last known in the list so you could do the algebra. All right. So now I'm going to reread the question because I've forgotten what we're trying to do. We're trying to determine the max distance between the cop and the speeder. So we're trying to get D. Got it. So I'm going to list my knowns, unknowns. By the way, I know from experience, if A is equal to 0, we only need distance equals rate times time. So there we go, right? And so I could write those other equations, but because A equals 0, you basically get V final equals V initial, which we already have used. So again, if A equals 0, this is your only equation, distance equals rate times time, which makes sense. When we started this chapter, I said that this long equation was basically distance equals rate times time on steroids, right? It gives you the next level, the next correction to distance equals rate times time. Well, if your rate is constant, you don't need the correction. Done. All right, so there's this equation, nothing to do there. And maybe I'll put a time 1 here, okay? Now I'm going to go into the red side. Well, for that one, I know that, right? Well, in this case, this one starts from rest, so that drops that out, and I get this equation. But shoot, I have 2 different times here. Is that going to be a problem? What do you think? Let me rephrase. In this particular problem, why is it okay to just erase the time subscript? And they have the same time in this problem. At this moment, they started at the same time. So we know that they're going to drive for the same time. So that's why I can actually drop the time subscript And so we don't want to willy-nilly do that, right? Like in the last problem, the two stages didn't have the same amount of time. But in this particular problem, we know T1, T2 is equal to T1 because they were driving for the same amount of time. That's implied in the wording of the problem. Basically, the cop started at the instant this one passed. All right. So at this point, which of these are we trying to find? Are we trying to find X2 or X1? Which one's more important? Or what are we trying to do? Zoom. All right, I'll help out. I feel bad for you guys. Sorry, I should be waiting longer or something, but I don't know. I just can't. I can't get any kind of feeling through the Zoom, you know. All right, we're looking for D, right? How does D relate to these two things? Let me say it that way. How does D relate to these two things? Can you give me an equation?
Would it be delta x1 minus delta x2?
Exactly. So delta x1 is the larger distance traveled by the speeder minus delta x2, and that should equal the distance between them. Now, I'm going to ask you guys, I want you to think to yourself, I've been saying distance, distance, distance. Is that okay for this problem? And right, because aren't we supposed to be saying displacement? If it is okay, why is it okay? What do you think? Why is it okay to use distance instead of displacement for this particular problem?
They're traveling the same direction.
Yep. And do they ever reverse? Oh, yes. Good. Somebody got it in the chat there too, because they never reverse direction. And so, so Erica was saying basically they're all going the same direction. And that implies that they're never changing direction, which I agree with. And so all of that is good stuff. Good job. So I'm just trying to point out that I'm saying distance because it's okay in this case. It's not always okay. Most cases when things reverse direction, for example, a lot of times with balls going up and down, right? When you throw a ball up, the distance traveled and displacement are not equal because it comes up, then back down, it reverses. All right, good enough. At this point, let's see how many equations and how many unknowns we have. This thing is known, unknown, 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 known, same unknown, same unknown. Take a look, and this is what we're looking for, right? So let's see. T, I don't think we were told T, right? Ooh, so we're in trouble here. Crap. How could we get the time, right? Look, we have 1, 2, 3, 4 unknowns. Agreed? There are 4 things we don't know here. X1, T, X2, D. That means we have only 3 equations. We can't get the job done. What's another equation we could use? It comes from the red side. Just go down and list all of our equations. We didn't do that, right? And there it is. I know that this is 0. I know that this is V equals A2T. Aha! I could use this equation to get the time. Right? Oh, whoops, AV. Yeah. So this would tell me the time that it takes. From there, I could plug that into here and get X1 and X2 and finally get D. Now, I have no idea how hard this is for you guys right now. This probably seems very weird because you notice I keep doing these check marks to remind myself, this is a letter that I know, this is a letter that I don't know. right? And so when you're reading the word problems, how do you know what gets a check and what doesn't? Let me just share the screen. In this case, this was given in the problem. It's a known. This was given in the problem. That's a known. And so notice those are the only two things they gave us other than, oh, from rest, that says V2 initial equals 0, right? Let's see, what else? Notice here's the statement. At the instant the speeder passes the cop, blah, 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 the cop accelerates. That's what tells us T2 is the same as T1. All right. And so, all right. And these words right here, maximum distance, that's what tells us V final of the cop, or V2 final, equals V, which was V1, the speed of V1. Okay. All right. So that's the idea. I'm going to leave this up on the screen and pause for questions right now. So notice every single detail in the problem, for the most part, is important, right? I guess there's a few little bits that aren't, like, we could care less if this is a snail, right? And we don't care about that. We don't really care about this. We don't care about that. And then let us call this point the origin. That's kind of nice. So then you could just say that, okay. But for the most part, you have to read this question carefully, and there's a lot of details that you are expected to know from practicing problems that help give you like zeros and which things are known and unknown. Okay. While we've got this, what does this mean? What does this tell us in part B? How far when she overtakes the speeder, when the cop overtakes the speeder, that's going to tell us something. What does that tell us? She would be going faster than the other car. Otherwise, she wouldn't catch up. I agree with that. That's one thing that's true. There's an equation that this tells us. So I want to be clear here. These words right here, this maximum distance between, tells us this equation. That's what we got out of that. We got a piece of information. So what do we get from how far from the origin? If the cop overtakes, I'm going to have to go back to my, hold on. What would this mean if the cop overtakes, right? This guy's going ahead, getting ahead. Finally, they catch up to each other, right? What kind of equation do we get out of they catch up to each other? What does that tell us? What is equal to what?
Their distances are equal to each other?
Yes. And again, we could strictly say, we should be saying displacement, but it's fine because blah, blah, blah. Okay. Now that's great teaching. It's fine because of blah, blah, blah. Oh my gosh, whatever. Oh man. Basically, if they catch up, delta x1 is equal to delta x2. That's what I was trying to ask you without giving it away. And great job fighting through that. So that's part B. All right. So in part B, we're told so what would you do? Start all over, do it again, except this time, instead of setting the times equal, right? Well, the times would still be equal actually, but you'd also set the distances equal. So I guess I should say in the first one, we set time and velocity equal. In the second part, in part B, you set time and delta x equal. So you got to be careful. When somebody catches up to somebody else, their positions are equal. If someone is at max separation, they are no longer gaining, they're moving at the same velocity. Gee, I wish we had a simulation for this. Jay, what do you think? Let's see. All right, class, let's see how Jay did with the no time to prepare challenge. Jay, should I let you share the screen now?
Yeah, I'll share it. And I actually cleaned up the code just a bit. Let me see if it's actually going to work this time. If not, I'll go back to the first code I did. Oh yeah, it's working. Okay.
All right. You go ahead and drive.
All right, let me share my screen.
Oh, I got you down.
All right.
Okay.
So this is the code that we did. Do you want me to try and explain the code or just show the
let's show the code, then explain it, then show it again. You know what I mean?
So this is the code that we have. So the blue ball represents the snail in the car and the red ball represents the cop. So they're
So when you click, the red ball will appear, or oh, they're on top of each other.
They're on top of each other. So, and that's actually one of the things I had to kind of mess with.
Yeah.
But when you click the simulation, it starts. So the blue ball is traveling faster, but the red ball will start to overtake it because the acceleration is not 0.
I got
So
you.
they hit. And so I made it stop at the point where it hits.
Yep, that looks great. Cool.
And then this is the graph of their positions. The red is the cop, the blue is the snail. And then I had it print the time or the place where it hits.
I gotcha.
And the time. And it's a code, so it's not exact, but.
Yeah. Do you want to go inside the code and kind of walk them through it a little bit?
So I actually used a lot of the code that you sent me, Professor Jorstad.
Yeah.
But this just, these lines right here, from like 1 to 16, those are all just setting the scene and the camera angle. So it looks a little better.
Yeah, it's Python.
I was having trouble because in my code, I wanted to make the code stop when the balls position were equal. So I had to actually set the red ball or the cop
right.
slightly behind.
I understand.
And it's like, it's 1 to the 10 times negative 200. So
you know what you could have done too is put while t greater than 0 and then you yeah, you like that one? All right. Anyways,
that would have been a lot smarter.
That's all right. That's cool. You got the idea. All right.
So I set the first, I set the position for the first ball. I set the velocity for the first ball and the acceleration. This is for the cop.
Could you hold on just a second? Don't move it. Yeah. So notice this is basically the X component. This is the X component. So these are the Y components and Z components that I'm scratching out. So the way we're trying to do these problems on the board should eventually match up to how you might do this in a computer program, everybody. Let me clear my drawings and let Jay have it back. Oh, go for it, Jay.
And so the first set, the one with all the ones, that's the cop. And so this is the second set. So I all set the.
I switched them. My bad.
I coded it flipped.
Yeah, that's fine. That's fine.
So
her 2s and my 1s are the same, and vice versa. Got it.
Right. And then all these print statements are just to look nice, telling you what everything, all the values were first. The sim speed just makes it go a little bit faster. So it's not the simulation is not moving too slow. And then the t equals 0, that's where we're starting it at.
Got it. So that's the instant that the cop passes the speeder.
Correct.
Mm-hmm.
And then our step size, just to make it smoother simulation, we did 0.02. Gotcha. I can make it smaller, and then all of these, these are fun.
Yeah. That's your grid marks.
These are, yes. So this is the x-axis, and all the line 1, 2, 3, 4.
Yeah.
Those are all the tick marks marking the 5
Cool.
positions. And then these 2 lines create the balls. So this is the first ball, which is the cop, and then this is the second ball, which is the snail. Then we go down to the velocities. This is a long code. This is just setting the velocities,
Yep.
creating the graphs so that we can mark the positions.
Yep.
And then this is the fun while loop. And I realized I duplicated the T delta T.
Oh, I see. I see. So let me ask you this. Can you go up to your ball positions when you first declare them?
Yes.
Yeah, right there. Oh, oops, no, down low,
Here.
right? Oh, okay, I got you. Can you offset one in the y-axis?
In the y-axis, yeah.
Yeah, just set one up by 1 unit. And so now, because you wrote your code correctly down at the end with the D, because you referenced the X position, setting them equal, try running it now. And then we could see this again. And then we should probably get back to, now we should be able to see them better, right?
Yeah.
And so the speeder's getting ahead, the cop is catching up, and now they catch up to each other. That's excellent. And then, all right, so that looks very cool. And just scroll down, your graph shouldn't be screwed up at all either, right? Yeah, there we go.
No.
All right, and so let's open this up to the students to see if they have any questions. We're just trying to help you visualize this and understand it. And let's go back to the gallery mode for a second. I'm going to stop your sharing. Let's see. Did that help you guys understand this a little bit, or no, or right on? Yeah, very cool. I'm going to give some thumbs up to Jay there or whatever or something. There we go. So let's give Jay a round of applause. That was pretty fast, Jay. Thank you for doing that in quick order there. That was good. All right. Jay, if you want to make that public to share with them, go for it. Just maybe throw the link in the chat. And then what you guys can do is, it won't allow you to edit hers, but I think you should be able to go into hers, copy the whole thing, and then paste it into your own Glow script, and then you could change the numbers on your own. Is that right, Jay? Yeah. So, all right. So that should work. That way, if you want to kind of get a feeling for this, you could try playing around with it. And you may not understand all of that, but yeah. All right. That's very cool. All right. At this point, we have covered this chapter. So we could be done, but maybe we should do one more question. What do you guys think? What are you worst at? Are you worst at the word problems? Oh, by the way, now that we spent all this time on this, the word problems that you're going to get on your tests are probably not going to be 2-stage. So we did that because I think flexing your muscles in the sense of working out harder than you need to do, I think you learn a lot from doing these problems like the cop and the speeder. That's more like a physics 161 test question. So yeah, nice Dom. Yeah. So yeah, anyway, so if these last couple of problems that we did at the start of class today freaked you out, that's okay. The problems on your test will probably be a little bit easier, but they'll probably be 1-stage questions for 110. Yeah, I mean, we could, in theory, say what are the types of questions you might expect, right? You're going to get some questions about graphing. You're going to have XT and VT graphs, and then you're going to have word problems, either horizontal or vertical. And most of the time, I can't remember if I used numbers or letters, or I may have done both. What's something I keep asking you about all the time, every time in class? What are things I'm picky about in class that you've noticed?
The difference between
Units.
distance and
Yeah, the difference between distance and displacement, right? So it's possible you might get a concept question about that, or speed and velocity, right? They're not the same thing. So there may be a concept question about that. Doing the algebra first, good. What's something I'm always harping on you to? Yes, checking the units, good. What else? This is all good. What's something I'm usually picky about, like all the time on everything other than the units? Not only the units, but also the, this is a terrible game. I'm thinking plus minus signs, right? Aren't I? I'm like always worried about you guys screwing up your minus signs, right? So there's probably going to be some questions that literally check, can you get the units right or the plus minus signs right? Okay. And most of the time we check units at the end. And to be honest, I don't know. That'll be something that appears periodically every once in a while on random tests. Okay. So checking the units, just, you're supposed to do that forever. And then also make sure you identify the signs right. So for example, I think I had a couple of questions where I literally wrote the questions and it was not your job to answer them. It was just which ones of these things are positive or negative kind of stuff. You know what I mean by that? Does that make some sense? Like imagine a question with multiple drop downs and it says, is acceleration positive or negative? Is displacement positive or negative? And that's worth a couple of little points. So you could expect a couple of easy concept questions like that. And then there's going to be at least one question where you got to do a whole bunch of algebra. And then some graphing questions. So that's kind of where we're at. Maybe I'll go to that. Any questions about that? I don't know if that helped you, Dom, there. Does that give you an idea of the kinds of questions you might expect? Yep, a little bit of everything. Yep. So it's probably about half on the word problems and half on the graphing. So you can't slack off on either one. Yeah. All right. Jay, any thoughts you have that might help them out since you're here? Any reflections you have on these types of questions that helped you study, or are you good?
I think what you were saying about doing the harder problems, it definitely does lock down the easier problems that you will give. Like if you can figure out how to do the stage 2 ones, then you'll be fine doing the stage 1 problems. It's
Yeah. Okay, cool. I appreciate that comment. Yeah, and it's not fun to do problems that you know are harder than the test, but it is fun to get a good grade. So, right, that's kind of the trade-off there, right? If you're training a little bit harder than you need to, it should be easier to get the A kind of thing. So, how about we do a graphing problem then? Just because we did a couple of these 2-stagers already, or yeah, would you rather do a graphing problem or another word problem? You call it. Throw something in the chat. Just tell me what you want and I'll do whatever you guys want. If you want to take off, you could take off, but we're just going to do extra practice now. The ones I recommend I gave on the list already. So that list of recommended problems is just, yeah, I recommend them all. Yep. A word problem. So Edgar likes the word problems. How about we do a vertical word problem? We haven't done one of those in a while, I don't think. So we did a horizontal, we did some graphing. How about we do a vertical word problem? I'll find one really quick. Maybe I'll find a vertical word problem that also has graphing in it. How about that? And just try and do everything. Oh, let's try 2.22. Oh, okay. There was a question about 232. Let me see what that was. Oh, yeah. So 232 is, yeah, we could talk about that maybe in office hours or something. All right. Or right after this. All right. So we've got 20 minutes. So we'll look at 232 next. Let's look at 2.22. All right. Let me bring it up. That was a good job, Jay, on that sim. Nice work. So if you're bored there, Jay, you could try and put that conditional statement, fix that conditional statement. So it's while t greater than 0 and position not equal or whatever. What did I say? 222? Oh, I just passed it right here. So notice this is a good one to do because we have already covered the plot. So it'll kind of put it all together. All right. So a rocket launched with an initial speed of 0. Initially, the thrusters are running and cause a constant upward acceleration with magnitude 2g. The rocket turns off its thrusters when it hits 98 meters per second. Then it's a free fall problem. What is the maximum altitude reached by the rocket? All right, so this is also a multi-stage problem. So this will kind of force us to keep everything all together. I'm going to draw a picture of what I think is happening, and then you, and look, we're trying to get to maximum altitude, right? So let's try and understand this rocket as it goes up to max altitude. You draw what you think, I'll draw what I think, and then if you finish ahead of me, look at the solutions. Oops. Okay.
Is this going to be a two-stage
Yep.
problem?
Yep. Nice. So this is kind of what I was thinking. I split it up into 2 stages there. We've got stage 1. And then I chose to call this part here stage 2. I guess my color coding, you notice it doesn't really matter, but I've just gotten lucky today where I've happened to always do stage 1 in blue and stage 2 in red, but that doesn't matter at all, right? So in this case, we start off, the acceleration is 2g. G is 9.8. So that tells me the initial acceleration is 19.6 meters per second squared positive because it's going upwards. I guess I'm assuming everybody is thinking the same way as me, which is dangerous. But usually people think X is this way and Y is this way, unless otherwise specified. So I'm assuming it's going upwards in the positive Y direction here. And that's why when the thruster is on, you're going to have a positive acceleration. It turns out, yeah, the force from the thruster must be 3 times as big as the rocket's weight. One unit of thrust overcomes the weight and balances it, and then 2 more units give it this upwards acceleration. But anyways, more on that when we get to chapter 5. So in this case, they happen to give us numbers. You could do this with letters or numbers or whatever. So in this case, if you wanted to, you could just call this V if you wanted to do that. So if we want to do this algebraically, we could just call that V. And then we've got G's and V's, and it should work out fine. Now, in this case, I know that at max height, that was another piece of information they told me. I know that this is equal to 0 at max height because that's where it reverses direction. It was positive velocity. It's about to come back down. I've got all my stages figured out now. So I know V2 initial in the y direction is equal to V1 final in the y direction. The initial for stage 2 is equal to the final from stage 1, which we said was V, which we said was 98 meters per second. You could tell we're not worried about sig figs here. All right. Notice the acceleration up here. After the thrusters turn off, gravity is pulling it downwards, right? It's wanting to slow down. And so that's why the acceleration is negative g up here. G is the magnitude of 9.8, negative because gravity is pulling it opposite this direction. All right. Any questions about that setup? What else do we have here? So I could tell I know V final. Maybe let's just make our list. It's kind of sloppy. So let me just make my standard list. Delta X2 equals, I don't know, V2 final Y equals 0. V2 initial Y is equal to 98 meters per second. A sub Y is negative 9.8 meters per second squared. And the time for stage 2 is, I don't know. All right. Down here on this one, getting rid of this coordinate system just because I need some room. Delta X1 is, I don't know. V1 initial in the delta. Oh, I should be calling this delta Y, shouldn't I? Sorry. It doesn't really matter, as you could tell. But let's be consistent. Sorry about that. This one's going upwards. I want to call it Y. That's a good habit to get into for the next chapter. It started from rest. This was positive 19.6. And so we could see what's going to happen here. I should be able to figure out this and this from stage 1. I should be able to figure out this and this from stage 2. This one's not that tricky, it turns out. We don't have to do too much work here, but we basically are doing 2 problems back to back. And so that's not too crazy. There's our list of knowns and unknowns. I usually think if you can get that done, the algebra is okay. It's all about getting the list of knowns and unknowns, getting the plus and minus signs right and the units right. All right, so on this one, was that okay? I'm going to look at the solutions to see where I went from here. You guys can chime in at any time, or you could chat with Jay if I'm going too fast and say, I don't understand him. That's fine. Okay. So it looks like there's a bunch of words, blah, blah, blah. This part we'll worry about. You could worry about that later. All right. All this later we will learn. You can worry about that later. So, okay, I used this equation to get 5 seconds for time 1. And then I figured out that it was 245 meters up using the delta Y equation. Then I had initial height was 245, initial velocity was 98, and now this is G downwards. It takes 10 seconds to reach max height. I use the V equation, and during that time it goes upwards. Look at that, a crazy 735 meters. Wow. Oh, that's the total height. So it goes up about another 500. All right. And so this is what your plot might look like for the XT VT. Let me make this a little bit smaller. So now you can see all of them. Let me make it a little bigger. So that's what that would look like. And notice the key time is right there. So before we see this positive slope, Here, AY is greater than 0. So you get a positive slope on the VT. And notice it's concave up. And here, A is less than 0. You get a negative slope. And you get concave down. And then the numbers I got from doing the problem. And so this is how you could take a graph and split it up into multiple stages. And if you're curious, you could do the same thing that we did before. You could actually get the area here. For example, this area would be a positive displacement because it's a positive area. And that would give you the change. That would be that positive displacement right there. It's the change in position. It's not the position. And so that's supposed to be this red area right here. Right? And then notice this, if we went past it and went all the way to the ground, this would be a negative area. That would be this negative displacement all the way here. That's that negative area. And if any of this is making sense at all, that's kind of cool, right? We're trying to see how reality relates to graphs. And in a dream world, eventually you'll get so good where you could look at the graphs and imagine the pictures doing stuff. And then if you had trouble imagining it, what would you do? You would write a simulation like what Jay just did. And it's going to take you years to get to that level to be great at all this. But probably by the end of next year, after you finish 161, I want this stuff to be so intuitive, it's just locked in your brain forever. I'm going to pause. I have no idea if this is a good or bad experience for you. It is physics, so one could assume bad. Let me see. Any questions at all here? Yeah, I'll be teaching 161, so you're stuck with me for a while, unfortunately. Yep. So let's see here. And again, I know this is probably hard for you right now. Like you don't want to do this. It's work. I'm not lying. This is a lot of work to do. But I will tell you this, the more of this work you do now, the easier the first 6 weeks of Physics 161 will be. So it's kind of like, man, I don't really want to do this. But if you could find a way, I mean, especially with COVID going on and we can't go outside and do fun stuff, maybe this is a good time to just suffer and do more physics problems. Although I got to tell you, it's starting to wear on me, like I'm sure it is on you. Not getting outside very much is just like, it's just depressing. But that's life, I guess. So I'm trying to do as much physics as I can now, hoping that that means later on I can go to the beach more or something, you know? All right. I'm going to look at Dom's quick question on 232, which is actually a pretty fun one to end with. I didn't, unless you had other questions before I get rid of this crap. All right, let's take a look. Whoops. What did I say? 232. And this is a good one to end on because we haven't done a lot with the AT graph. So let's take a look at an AT graph and just do one of them to be thorough. Did it go? There we go. All right, and so we haven't done a lot with these AT graphs. This one, I tried to make a more realistic graph. Usually more realistic means harder, okay? So that's just real life, but you could actually learn something from this. And this is surprising. I really love the first question here. So let's just try and take a guess and see what you think. We have an object that starts from rest. It's a car at a stop sign, right? And so this kind of looks like you rolling on the gas pedal, then rolling off the gas pedal, right? A little bit. Yeah. At what time do you think the object has the greatest speed? Exactly, after the full time. So this is crazy. Remember, acceleration by definition is approximately equal to delta V over delta T. And so think about this. As time goes on, anytime A is greater than 0 in this problem, V is increasing, right? In this particular case, because it started from rest. So in this case, because it started from rest, anytime A is greater than 0, it's going to be speeding up. And so A is great. It's speeding up, speeding up, speeding up. This is the most rapid rate of speeding up, but they're still speeding up, just not quite as much, speeding up a little bit less. And so this is sort of like you guys asymptotically approaching full speed. Once you get close to full speed, you find some equilibrium on the gas pedal where your car is moving at about the constant rate. So right here, the speed stops increasing. All right, that's cool. So that's kind of fun. Estimate the speed of the object at 4 seconds. Well, at 4 seconds, if I was right here, while this isn't exactly perfect, I hope you agree that the area that I'm missing right here is overcounted right here approximately. So if I just do a triangle here and get this whole triangular area, it's going to approximately give me the right what? What do you get when you do the area on a VT graph? Does anybody remember?
You get velocity, right?
Careful, I would say you get, it's not quite velocity, it's not speed. Delta V, which in this case, if V initial equals 0, then the area would also equal velocity. So in this particular problem, it's okay to say that the area would equal velocity. In general, that's a bad idea because what if it had initial speed? Then what you said wouldn't be true. I don't know who chimed in, but did that make sense of the subtle distinction there?
Yeah, it did.
Yeah, so you are right in this case. Good job. And then remember that in general, it should be delta V. So I guess the short answer is good job. All right, cool. And then how would I get the speed? Oh, I'll show you. All right. The speed is right at 8 seconds. You just double it, right? Because you have twice the area because you get this area. So then I want to get this question here. All right. So I know that you guys don't know calculus, but sometimes seeing the calculus really helps. So I'm going to show you with calculus, and my apology, this is not required, but if it helps you learn, it's worth doing. Okay. So the acceleration is equal to, by definition, it's the time derivative. So basically it means a rate of change. So the short version, if I just cross multiply and rearrange these things, it turns out that acceleration times a small amount of time gives a change in velocity. Or what if you want to view this approximately, right? This is approximately change in velocity over change in time. And so the idea here is acceleration times a change in time is equal to delta V. Now, if you don't like that, what I could do is just say, well, what if I rearrange this and integrate it, right? If I integrate these, I would have to go from, say, 0 to some time I'll call t final. Well, over here, that would go from velocity at 0 to velocity final. Okay, because if I go from this time, that corresponds to this velocity. So I'm doing the same thing to each side. When I do that, well, the integral of this would just be v evaluated at. And that's why. And this would be a, if we had constant acceleration, the a would pop out. And then we get the integral of dt evaluated at 0 and t final. Well, that's just v final minus v0 equals acceleration. This one just turns into t final. Well, gee, isn't that just our kinematics equations of constant acceleration? Now you know where they come from. If you integrate it another time, guess what you get? The delta x equation. We'll do that in physics 161. But somebody had asked a question about something. Did this answer it? All right. Oh, good. We'll just let Jay do the work there. Thanks, Jay. Okay. So what did I have something missed wrong or what's that, Jay? Oh yeah.
Oh, no,
delta
you
V.
didn't have anything different. You didn't have
Yeah.
anything different.
Right.
I was
and
just explaining it in a different way.
So yeah, you were saying that this right here is delta V, I think is what you were saying or something, right?
I wasn't saying anything to
Oh,
yours. I was
gotcha.
explaining it in a different way.
Understood. Okay. Yeah. All right. So this is probably a good time to call class since it's been over for 4 minutes and I didn't realize it. I'm going to stop the live stream.